All right, we good to go? You okay? All right, guys, we're gonna get started with our quiz 3 review. Again, Luke Langner. My name and email are here. There's 2 N's. Don't forget them. Everyone does. So if you have any questions later on, let me know. The sign-in sheets have been going around. Make sure that you get your name and your email on those, so I can send you all of this information after we're done. I'll make sure to scan everything in. There aren't any last-minute tips or anything on the sheets. So yeah, again, just make sure you get those at some point, and then I'll make sure to stick around for a couple extra minutes at the end, so that if you guys do have any other questions or you still need to sign in, I'll be here for that. Okay. So from what I understand, Bill has sent out a packet that looks a lot like this to you guys, right? Okay. My original plan was going to be to do this, but I'll leave that till the end if we want to do an extra problem or two, because you guys have those with the solutions already. So what I'm going to do instead is I'm going to go over I think this was my in-class quiz, yeah. But it's got a truss, it's got a frame, and it's got a centroid problem. And then I've got another moment of inertia problem in the packet that we can do as well. So we can really hit those 4 big topics for the test. Is there any topic that I'm missing? Trusses, frames, centroid, moment of inertia, right? Yeah, all right, okay, cool. So we'll start with the truss problem, if that's okay with everyone, yeah? All right. I'm gonna draw it over here. So what this problem gives, it gives you a truss, gives you the reactions, and it's just asking you to find a couple of member forces. So I'm just gonna draw that real quick. Sorry, I'll try not to stand in front of it as I draw. Is this okay? Is this big enough for everyone? Can everyone read the numbers and everything? See the figure? K is kips. I'm just too lazy to write that out every time. So K is kips. Yeah. Bless you. All right. Well, you guys are writing that down. Oh, you guys did this one in class? Shit. Okay, do you guys want to go over it again? Yeah, I have some yes, some. Nah. Yeah? This exact one was on the short quiz for Billa? Interesting. Some of the other classes didn't have it? All right. So we'll work through it just to make sure, just to reinforce the concepts, and just because not everybody had the same problems. Again, focus, I guess not so much on the problem then, but if you focus on the process itself, again, it's the same problem. It'll be the same process for every type of problem. Additionally, I'd like to give a shout out to Evan up here in the front. We'll be filming this for you guys tonight so that you can have this to watch over, like with Kevin. Is that Kevin Ryan? Yeah. Round of applause. So a big thank you to him. How are we doing? Has everyone been able to copy the diagram down? All right. While you guys are finishing that up, I'm going to start talking about the problem. Okay, so the question reads, for the truss shown, the reactions are given. So you've got this reaction at point E. It's a vertical reaction just because it's a normal reaction because it's the roller. And then we've got the pin at A. So we have the vertical and horizontal components of the reaction. And then it's asking you to find the member forces in BC, HC, HB, and FE. So I'm going to mark those. So it's asking you to find the member forces in members BC. Wow, that's awful.
You guys see that? A little line right there? No, not if-ish. All right, I won't write too much of this. I'll just mark stuff. HC, HB, and FE. All right. So what we're going to do here to start is we're going to use the method of cuts. All right, so we've got three members right here where we want to find the member forces, right? So in order to get those member forces, we're going to have to do cuts through the members in order to kind of let them out so that we can see how they're interacting with the rest of the body. So when you're doing your member cuts, your goal, you want to cut as many of the ones of your goal members as you can. So we want to cut through as many of these that are marked without cutting too many that are unnecessary. So I don't want to do a cut straight across here because that's going to be cutting 1, 2, 3, 4, 5, 6, 7 members. And that's going to be giving us 7 unknowns that we're going to have to solve for when we're doing our problem. So we want to minimize the number of unknowns that we're introducing, but also make sure that we are cutting members that we're trying to find. Does that make sense? All right, so the cut that I'm going to do is I'm going to do a cut straight down between these, just like that. I'm going to call that cut AA. So here I'm cutting through 2 of the members that we're looking for, and then additionally cutting only 1 extra member so that I'm minimizing the number of unknowns that I'm bringing out, but I'm also making sure that I'm bringing out 2 unknowns that I'm definitely going to be looking for. Does that make sense to everyone? Why we're cutting there? All right, cool. So I'm going to draw that section real quick. I'll draw that, or I'll draw it over here. So we left this entire triangle intact, right? So we've got A right here. With this, I just drew right over that with its 30 kips to the left and 50 kips up. Got a distance of 15 feet here, 40 kips down at B. And then, so this is where our cut is, right? So this is member BC right here. So we're going to have force BC coming out. We're going to have, this is point H right here. We've got 30 kips coming out as well. I'm sorry, I have that backwards, don't I? 30 kips coming in, acting to the right. We're going to have force HC, member force HC coming out of here. And then up here, we're going to have member force HG going in like this. So the direction of the forces is, I know, another big topic that is stressed when you're doing this type of problem. The forces, the way I put them here, are mostly random because I know the solution already. But when you're doing a problem like this, the direction of the arrows, and it's similar to a lot of other problems that you've done where the direction of the arrows when you start doesn't matter as long as you make sure that you account for that in your answer. If you get a negative answer, you know that your arrow is facing the wrong way. Does that make sense? Does everyone remember that concept? It's something we use in a lot of different problems, even going back to quiz 1. So again, arbitrary assignments for the directions. Just remember to switch the direction of the arrow if you get a negative value for that member force. Everyone cool with that? Yeah? All right, cool. I think I wrote everything on there correctly. Yeah. Okay, awesome. So we're going to start and go into actually solving this for the member forces. So the 2 member forces that we're trying to find out of this one are force HC and force BC, right? Because those are the 2 members that we were asked for before. Those are the 2 that we're going to try to find from this one. So looking at this diagram, we've introduced 3 unknowns. What we want to do is we want to either do an Fx or Fy equation or a moment equation that's going to eliminate the number of unknowns that we're using. I'm sorry, minimize, not eliminate. Minimize the number of unknowns that we have to work with. So if we're looking at doing either an Fx or an Fy equation, we do Fx, we have force BC, we also have the horizontal component of this force. So that's 2 unknowns. So let's look at Fy. We do Fy, we've got just the vertical component of HC, right? So we'll start with that. We're going to do summation with up being positive of Fy, and we're going to assume that it equals 0. Then from there, we're going to get 0 equals, looking at this entire diagram, we've got 50 up here, right, at point A. So 50 kips up, 40 kips down at point B, And then we've got our y component of force HC. So I'm just going to call that force HC y for now. Is everyone okay with that? With why I'm doing that? All right. So solving for force HCy gives you 10 kip. 10 kip, yes, I can do math. Also, feel free to check me along the way. If anyone's come to my reviews in the past, I've been known to make stupid mistakes, like not adding that correctly. So please feel free to check me, or just trust me, that works too. Yeah, so that's what we're getting for our y direction of force HC. Oh, we've got a non-believer up here. He's got his calculator. I'm just kidding. Fine. That was funny. I thought that was funny. Whatever. So we got a positive number. That means that my force is in the right direction, or at least my x component is. Or the y component, I apologize. So, yeah. Now we're going to look on to doing the x component. So if we look back to this diagram, we're looking at member HC, right? That's this member right here. We know that each of these segments is 15 feet across, so this is 15 feet. And we know that this truss is 20 feet high. So from this, we can make a 3, 4, 5 triangle, right? Because this is just 3 times 5, that's just 4 times 5. So we know that the hypotenuse is just going to be 5 times 5 for 25 feet long. So with the 3, 4, 5 triangle here, we could say that the x component of force HC is equal to 3/4. Sorry, I can't write a 4. 3/4 of FHC, the y direction, which is going to give you 7.5 kips. Does that make sense to everyone why that works? Yeah. All right, cool. And then in order to find the magnitude of FHC, you can do the square root of the x component plus, I'm sorry, that should be an x. Oh no, that should be y. Ignore me. We're going to do the square root of the y component squared plus the x component squared. And that's going to give you 12.5 kips. Now, another way that you could have done that, yeah, what's up? No, so since we're taking the x directly from the y, it's going to be 3/4 because we're not looking at the hypotenuse right now. So what you could have done is if you wanted to not do this, if you wanted to skip this step and go directly to the hypotenuse, you could have said, okay, I know that the y component is 4/5 of the hypotenuse, so you could have done FHC y equals 4/5 of the hypotenuse, which is just FHC, and from there you'll get the same answer. Sorry if my handwriting is terrible, but that's another method, another way of doing the same thing. Is that along the lines of what you were asking? Yeah, okay. Does that make sense to everyone? Just do both methods? Make sense? Yeah. All right, cool. All right, cool. So there's one of our answers. So we've got our member force and member HC right here, so we can check that one off. So we've still got another member force in this one that we're trying to find, right? We're still looking for force BC. So we already looked at doing a force analysis in the x direction, and we said that that wouldn't work. We've done our force analysis in the y direction. We can also do a moment, right? And what we want to do with our moment is we want to eliminate, take the moment at a specific joint, so where we're minimizing the number of unknowns we have, but still making sure that we're looking at, that we're going to be using the unknown that we're looking at. Sorry if I'm blocking the board. If I'm blocking the board, just like raise your hand, tell me to move. So again, I'm going to come over on this side so you guys can still copy down that middle part. We've got 3 unknowns here, right? And we're looking for this one. This is our last one here. If we take the moment around point H, we eliminate any moment effect from force HG, from member force HG, right? Because if the line of action of a force lines up or passes through the point about which you're taking the moment effect is 0, right? And same thing with force HC, the line of action for both crosses right through that point H. But force BC, the line of action is down here. So we can take that moment and get force HC. Does that make sense to everyone why we're picking point H? Yeah? All right, cool. I'm going to move over to this board. I'll put my email back up at the end if you guys want it, but I'm going to erase this for now. And so we're going to do The summation, I'm sorry if I'm in your way over here. The summation of the moment about h, we're going to assume counterclockwise is positive. I'm going to set that equal to 0, right, because the truss, we're not moving. You're going to get 0 equals, so if we're taking it about h, first one that we're going to look at is that 30 kips on the bottom there. Sorry, whoever wrote this solution guide got their signs wrong. That's okay. So we're going to look at that 30 kips on the bottom here. So if we're taking the moment around h, this 30 kips, sorry, kind of squiggled, there we go, is going to the left. That's going to give us a clockwise circle, right? So that's going to be a negative moment. Is everyone cool with how we found that? Is that okay with everyone? Yeah? All right, cool. So we've got negative 30, and it's acting at a distance of 20 feet away, right? Because that's the height of the truss. That's the distance between the line of action of the force and from the point about which we're taking the moment. So we've got negative 30 times 20. We're also going to be looking at the 50 kip force that we've got here acting vertically at point A. So again, same thing with this point, with this force acting around point H. We're going to have a clockwise moment. So we're going to end up with the same, with another negative moment. So it's going to be minus 50 at a distance now of 15 feet, right? Does that make sense to everyone? Because this line of action is here, so we're going to use this distance. Whereas with the 30, we were using this line of action, so the distance was 20. Does it make sense to everyone why we're using the distances that we are for each force? Does anyone want me to say that again? No? All right, cool. So that's going to be 50 kips at a distance of 15 feet. And then we've got force BC down here. We said it's going to the right. So that's just our assumption. We're going to give it a counterclockwise moment. So that's going to be a positive moment plus force BC. That's member force BC at a distance, again, of 20 feet. And when you solve all that out, you're going to get that member force BC equals 67.5 kips. Is everyone okay with that? How we use the moment equation there? How we picked our point, found our forces, found our distances, and the signs for the moments? Does anyone have any questions about anything that we've done so far in this problem? Everyone good? All right, cool. Is everyone all right if I erase this middle part here, this middle board? I'm going to move on to the next two member forces with that. Everyone's got this? All right, cool. Is everyone able to see everything that I've been writing? Like if I write any lower, is that going to go out of your vision, or are you guys going to be able to see that down here? Everyone's good? Look mostly at the people in the back. You guys up front are good too if I write like down here at some point? Okay. I'll do my best to keep it as high as I can, but yeah. All right, so for the next point. So we just found member force BC, right? So we've got this one. Now what we're looking for is member force, the force in member HB and the force in member FE, right? So those are the last two that we're looking at. So for these cases, we could do another method of cuts, but we don't even need to do that because any method of cuts that we would do, if we were to do this, or if we were to do, I don't know, if we did something like this one is going to release a lot of different variables that we don't need, unknowns that we don't need to be working with. And I'm sorry, down here we would do, that would make a lot more sense. And for this one, cutting here, and for that one, that essentially just leaves us with a point. So you can do a point analysis for these two at points at point B and at point E, which is essentially the same as just making these two cuts. Does everyone understand that? So it's, yeah.
Is the moment last problem, if you do point analysis on the limit value for
So if you did a moment analysis at point B,
the point analysis, point B, the analysis of the X.
you do the analysis of the X component at point B. So in order to do that, we would need the value of the member in force AB as well. And to do that, you'd have to go into either point analysis or cut analysis if you did a cut like this, or if you did a moment analysis there. So you'd have to, you should get the same value though. So the question was, if we did a point analysis at B and did Fx, would we get a different value for the member force in BC? The answer is that no, you should get the same value regardless of the way you do it. It's just you might get it through different methods. So like we found it via the moment before. This way, if we did analysis at point B, we'd have to do summation Fx, but it should give you the same value every time. Does that make sense? Does that answer your question? Yeah. All right, cool. Any other questions so far? All right, cool. So we're going to look first at joint B. So looking at joint B, that's right here. We've got, I'll draw it over here. We've got our 40 kips going down. We've got force BC, we said was going out before, and we were correct with that because we got a positive number. We've got force HB going up. And again, we're just making that assumption. With only two vertical forces, it makes sense for one to be up and one to be down. So this is one where you can easily just say, like, logically, does that make sense? Yeah, what's up? Yeah, it is. I'm sorry. I just didn't draw that very clearly. Sorry about that. Thank you. Is everyone? Yeah, sorry about that. I'll make sure I write more neatly. And then we've got force AB coming out here. So again, we don't know the direction of these two forces, right? We know this one's down, and we found that this one was correct because our value that we got was positive for that. We don't know those directions. In a problem like this, it's a little bit easier, to see that you need to have the values going in opposite directions to make everything equal 0. So for this, we're just looking for force HB. That's the only one that we're asked to find, asked to solve for in the problem. So we're going to do another summation in the y direction. So summation of Fy equals 0 with up being the positive direction. You're going to get 0 equals FHB minus 40 kips. And that's going to give you FHB equals 40 kips. Does that make sense to everyone? Pretty straightforward. And then we're going to move on to joint E. And we're going to do the same thing. So we've got our 70 kips going up. Right? Do I have that right? Yeah. So you've got your 70 kips going up. You've got force DE, we could just say is going in. And then we'll say that force FE is going out. So let's just for fun, we'll say that force FE is going out. So again, same triangle as we've got before. We've got this 3, 4, 5 triangle because we've got 15 feet along the bottom between those two, between points D and E. You've got 20 feet between points D and F. That means you've got 25 between E and F. So we've got our 3, 4, 5 triangle again there. Is that cool with everyone? Yeah. All right. Awesome. Nice. So again, we're looking for force FE. We don't know DE, so doing a force analysis in the x direction isn't going to help us. We're just going to end up with an equation with two variables. Doing a moment analysis isn't going to help us because everything's acting at this point. So we're going to end up with just 0 all around. So we're going to look at doing a summation in the y direction. So with up, summation in the y direction of the forces in the y direction equals 0, with up being the positive direction. And we're going to get 0 equals 70 plus 4/5 FE. Force of FE. It's supposed to be an arrow. I'm just going to erase that. So when you solve this, so again, this is because we said that these were both facing up. When you solve this, you're going to get that force FE. It's going to equal negative 87.5 kips. That just means that our direction was wrong. So if we were to draw it this way instead, we would get positive. Does that make sense to everyone? Yes? So this problem does not specifically ask for compression or tension, but yes, we can look at a problem. I know that the first one on of the 6 problems that you were given asked you to state if they were in tension or compression. So yes, you would. You guys want to look at that real quick, at least for, I know I erased a lot of them, but we can at least look at it for these two. Yeah? All right, cool. So looking at bless you, joint B. I'm sorry, joint B. We're looking at force HB. So we put force HB, that's a force acting right here. We said that it was pointing upwards, and we got a positive answer, meaning that our direction is correct. Now, this is always one of the most difficult concepts in MechSolids to understand, is the difference between whether a member is in tension or compression. So, if we say that the member force, this is a force just within the member, we're saying that it's pulling inwards. That's going to mean that it's in tension. So a good way to think about that is if I'm pulling at this marker, I'm pulling it, it's in tension, right? But the marker itself wants to stay closed. There's friction here that's pulling it in. So it's fighting me pulling it outwards by having an inward member force. That makes it in tension. Does that make sense to everyone? I know, because a lot of times people see inward force, they say compression. But you can think of that as the reaction to the forces that are being acted upon it. So in reality, this member is being stretched, it's in tension. Its reaction is it doesn't want to move. It wants to stay its same length, keep its properties, whatever. So its member force is going to be pulling inwards. So it's in tension. Does that make sense? Does anyone have any other questions on how to figure out tension versus compression? Yeah.
Draw like a good picture of the member and then like break cut it at either end and show the forces of the internal forces and the joints.
Yeah, you want, yeah. So we're looking at a member here, right? We'll cut the member right down the middle. So I don't want to like lean over. So we're looking at it here. If we apply a force on the outside, this member is in compression right now, right? We're compressing it. Its reaction, if we just look at this left side, which way is the member force going to be pointing? It's going to be right. It's going to be going towards the outside. It's going to be pointing towards the left. And then if we were to look at just the right side, the member force is going to be pointing towards the right. Right? If you were just doing a simple FX analysis, that's what we're going to get. So that's telling us that if a member is being compressed, it's going to push out. It's going to say, no, I don't want to be compressed. I want to stay the way I am. And we're going to end up with that member force. So the member force is going to look like that in this case. And then the reverse is true if it's in tension. If you've got a member that's being pulled in tension, the reactant forces are going to be pulling inwards, saying, no, I want to stay my same size. Don't pull me apart. And your member forces are going to be going inwards from the joints. Does that help? Yeah. Is that diagram more helpful? I'm always trying to find a good way to explain tension versus compression. So thank you for that idea. Does that explain it for everyone? Why the difference between tension and compression? That was a really good way to think of it. Thank you very much. Yeah.
We get a negative number, like when we're finding forces that we just found just now, like how E7 was negative. Does that mean it's just the wrong direction, or that it's in compression?
So in this situation, it meant that our arrow was in the wrong direction. That's the only way that we were looking at it in that sense. A really good way, and I'm glad you brought this up, a really good way to do these problems is when you write your member forces, if you assume them all to be in tension. If you, is everyone okay if I erase this board? I'll draw my example over here. Cool. If we look real quick at the AA cut that we made before. Right, we had something like this. If we assume, right, if we draw all of our member forces like this, that means that they're all trying to pull in. They're all in tension right now. If we make that assumption, if you make that assumption in all of your problems and you get a negative number, you can automatically say, oh, it's in compression. That's a really, really great way to check your answers. That's even if you don't understand tension and compression, if that example doesn't make sense to you, and you just want a way to do the problems and get the right, get tension or compression checked, that's good. Have all your member forces going out. Positive means tension, negative means compression. Does that make sense to everyone, how that works? If you want to have your arrows going the other way, that works too. Whatever works for you as long as you understand it. So that's a really good check, as long as you make sure that you're assuming everything's either in tension or compression. Because if you draw something like this, now you're assuming these are in tension and that one's in compression, and then getting a negative for what makes which one tension and what compression, that'll get confusing. But if you assume them all in tension or all in compression, that's where the positive negatives can really help you. So that's a really, really good trick, a really good tip for this test especially. And that'll come in handy on the final as well. There's usually some form of probably a little bit more complex frame or truss on the final that you'll see potentially both. So that's something really good to keep in mind. Does that make sense to everyone? Yeah. All right. Cool. And that's it for this problem. Did anyone have any questions on anything we did? How we picked again? How we picked tension, compression, finding moments, picking points to picking members to cut, how to define member forces, magnitude of a member force, anything like that? No? All right, cool. Are you guys all right if I erase everything? Is anyone still copying? All right, cool. And I hope that those of you that did see this before, that you're still getting something out of this. So I'm actually going to do the second problem here. The next problem we have is a frame. But what I'm going to do is the problem gave you the reactions. And what I'm going to do is have us find the reactions first. And then we'll go through the problem together. Is everyone okay with that? We'll throw in that little extra step there in case he gives you a problem where you have to find the reactions and then do analysis. Most times, he'll give you the reactions. That's a question that a lot of students have, is are we going to get the reactions on the quiz? You do get them a lot of times just because he doesn't want you to spend time doing FX, FY moment analyses on an entire truss or an entire frame all the time. He knows from the first or second quiz that you can do that. He's testing more of, can you do truss and frame analysis? But if it's a bit of a lighter problem, he might have you find the reactions just to throw you that curveball. So don't blow it off, but I wouldn't expect it. All right, so we've got our frame. All right, cool. So there's our frame. I drew it a lot more simply than it is here, because this one, I'm not an artist. I'm just going to draw the basics. I'm just going to draw that simply for you. What we've got is we've got a pin and roller bases, and then points. Pins A, B, sorry. Got our pin at A, our roller at C, our joint, bless you, at B. Then we've got a 75-pound force acting 8 inches away from joint A, and that's acting on member AB, and then we've got a 50-pound force, acting 6 horizontal inches away from point C, and that's acting on member BC. Is everyone okay with that? All right. So, what kind of reactions are we going to have at point A? AYAX, exactly. So we've got AY. I'm sorry, that's AX. My apologies. And then AY. All right, is everyone okay with that? You have the pin, it's not rolling in any direction, so we're going to have the reactions in both directions, horizontal and vertical. And then what about at point C? What kind of reaction are we going to have? Say again? FC, right, but in which direction? Horizontal, right, exactly. So we've got a roller here, which means that it's free to move in the y direction, but it's not free to move in the x direction, so it's going to have that horizontal component of its reaction. Is that okay with everyone? We're going to call that CX for the purposes of this problem. Okay. So we're going to do either Fx, Fy, or moment. My tip, start with moment. It's almost surefire way to get you at least one of them. So again, similar to the last problem, we want to make sure that we take the moment about a joint or around one of the points. That's going to eliminate as many unknowns as we can while still giving us trying to get that number of unknowns as close to 1 as we can. So if we take the moment around point A, we're going to eliminate the effects of the moments of AX and AY, and we're just going to be looking at the effects of the moment of CX. Does that make sense to everyone? All right, cool. So we're going to do summation, the moment about A equals 0, and that's going to equal, so we've got, oh, bless you. No, I'm sorry, we've got counterclockwise is positive. So what we've got is first off, that 75 pounds, it's going down, and then relative to point A, that's going to give us a clockwise motion, right? So we're going to have negative 75 pounds. That's acting at a distance of, the line of action is at a distance of 8 inches, right? So that's negative 75 times 8. And then we've got our 50 pounds also acting downwards. So that's also going to give us a clockwise motion. So that's going to be negative 50, sorry. What's our line of action going to be for that one? 6. I heard a 6 in the back. I didn't give you many options either. But yeah, it's going to be that 6 because even though this is, it's acting at this distance from A, right? That's not going to be the distance that we're using because we're looking at the distance between the line of action of the force. So the distance between that line of action and the point. So A is right here. Looking for that, the perpendicular distance really is the key word there. So this is the distance we're looking at, which is that 6 inches. Does that make sense to everyone? All right, cool. That's another difficult concept to grasp. And then lastly, we're going to have our reaction at C. It's going to the right, so that's going to give us our counterclockwise moment. So that's going to be positive CX. And that one's acting at a distance of, I didn't write it on the diagram. That's my bad. I know, I'm sorry. That's acting at a distance of 5 inches. Yeah. Okay. So is everyone cool with that? How we got those distances and those forces and their directions? Everything? All right, cool. So that's going to give us CX equals 180 pounds. So that's going to be our reaction at C. So I'm going to go over, if you're all okay with that, I'm going to erase this, and I'm going to put 180 pounds here. Now what we're going to do next, looking at the only unknowns that we have left are the reactions at A, the horizontal component AX and the vertical component AY. It's really have one of each. It's really simple, really easy to just do X component analysis and then Y component analysis. So if we're looking at summation of forces in the X direction with right being positive, I'm going to set that equal to 0. You're going to have CX minus AX, right? Which is just, we already said that CX is 180 pounds. That one is super simple. You're just going to get that AX equals 180 pounds as well. And notice that we're getting positive answers, right? That means that the directions we chose were correct. Is that cool with everyone? Then we're just going to do summation of forces in the y direction with up being positive. And we're going to set that equal to 0. And we're just going to get that, we've got that positive AY minus 75 minus 50. That's going to give us that AY equals 125 pounds. And again, positive answer, we have the right direction. It's almost like I knew which way they were supposed to be before we did the problem. Is everyone okay with that, how we found those 3 reactions? Yeah, any questions on that? Everyone's got that down? All right, cool. Again, you shouldn't, I don't think he'll give you a problem where you have to find the reactions, just because, again, he wants to test how you can do with frames and trusses. He's not trying to test, can you do moment fx, fy over and over again, even though that's still a lot of what you end up doing. Yeah. You'll likely be given the reactions. So we're going to look forward. So this is how the problem was actually presented when it was actually given. Is everyone okay if I erase this middle board here? Yeah? All right, cool. If you didn't get the forces there on the diagram as well. All right, okay, cool. So the actual question states a frame is loaded as shown. The reactions at A and C have been calculated, which we just calculated. And it's asking you to find all the forces for member AB. So it's asking you to find all of the forces acting on this member. So does anyone want to shout out what our first step's going to be? Anyone? Any thoughts? Free body diagram. I heard it somewhere. Free body diagram. There it is. All right, cool. So the first thing you're going to want to do, if it's asking for all the forces on a member, draw that member. So we're going to do our free body diagram of AB. So we've got A here, so then we've got B here. It's not exactly aligned, but it's fine. We know that we've got our 75 pounds acting downwards right here, right? We've got that at a distance of 8 inches. Additionally, it gives you a dimension of 4 inches there. I'm sorry, I missed that over here as well. I'm sorry, I swear that's it. I swear you actually have all the dimensions now. Sorry, my apologies. All right, and then again, we have our reactions. At A, we've got 125 pounds up and 180 pounds to the left. We have 2 more forces acting on member AB, and they're going to be the member force in AC and the member force in BC. Does everyone get where we're getting those? Because they're going to have that interaction between the members as well, so we want to make sure that we account for that. So what we're going to do is we're going to put the, bless you, we're going to have force AC right there, and we're going to put force AB over here. And one thing that you can do right off the bat is, we didn't do this in the last problem, so I'm just showing you a little bit of a different way to do it. If you don't want to worry about your triangles, which you don't have in this case anyways, you don't have that 3, 4, 5, what you can do is split this up immediately and do like, oh, okay, so like we've got BX, we've got BY, so you could just like find those individually. Yeah, cool. Yeah, lots of hands. We'll start over here. Yes, thank you. Is that what all the hands were? Gotcha. Oh yeah, we got one more.
So there's a question asking that you're solving for the forces in that. So would it be okay if you just solve for FCB, right?
Yeah.
And if you just put your answer in just FCB, or do you need to put it break it up into 2 to solve for it? Like how would they accept my answer?
So either would be accepted. It's definitely going to be a lot easier to break it up into 2 and to do them separately. My suggestion would be to separate it into 2, and then at the end do that whole square root. Take the actual magnitude of the force and put that as your final answer. If you have all 3, you can't be wrong. Yeah. give them everything, then they can't take off points because you're not wrong then in that case. It's definitely going to be not difficult. And actually, I'm sorry. We don't have a 3, 4, 5 triangle. What we do have is a 5, 12, 13 triangle. It's another Pythagorean thing. So you could just do, just work with the hypotenuse like that with like the 5, 13s, 12, 13s, 5, 12s, whatever. That could work as well. It's just a matter of personal preference. It's just, just for the sake of doing it a different way, I'm just going to do the splitting up. But whatever works best for you. Okay, so these are all of our forces that we've got acting. Does everyone understand what we were just talking about whether or not give it in components or to give just a total force? Yeah? Cool with that? All right, cool. So what we're going to do is we're just going to do our equilibrium analysis again. We're going to start with a moment. And taking the moment around either point, since we've got 3 unknowns, right? We've got Bx, By, really those both make up FBC, and then FAC. So if we're just looking at these 3, because this can just be a component of the other 2, taking a moment around either point is going to give you a solution that you want because both are going to eliminate Bx, right? Because whichever one you take the moment about, it's not going to have any effect. So just for the sake of moving forward, we're going to take the moment around A. Yeah, the moment about A with counterclockwise being positive, we're going to set that equal to 0. And then we've got 75, it's giving us clockwise, so we'll make that negative 75 at a distance of 8 inches. And then we've got By, we said is, it's going to give us, it's up, clockwise, positive, By at a distance of 12 inches. And then from there, we're going to get that By equals 50 pounds. And we know that our direction is correct. From there, you can do summation of forces in the y direction with up being positive. We'll set that equal to 0. And then we'll say negative force AC plus 125 minus 75 plus, now plus By, which we just found to be 50. And that's going to give us that FAC equals 100 pounds and positive, our direction was right. Everyone cool with those 2 so far? All right, I'm going to move on to, I'll write it up here. Then we're going to do our summation of x, of f in the x direction. We're going to set it equal to 0 with right being positive. We've got our negative 180 from the reaction at A that we found before. And then we've got our positive Bx. And that's just going to give us that Bx equals 180 degrees, not degrees, I'm sorry, pounds. Is that cool with everyone? Does that make sense? All right, cool. So again, another way that you could do it is, we've got a 5, 12, 13 triangle here, so that's 13 inches there. That's just another good Pythagorean triangle to keep in mind is the 5, 12, 13. So one thing that you could also do is look at this and say 5, 12, 13, and if you just to find FBC, you could say, looking at the moment equation, you could rewrite it as this. So we've got, again, counterclockwise positive summation of moments about A is 0 equals negative 75 times 8 plus 5/13 FCB. Oh, bless you. And we know that that's positive, and we've got the 5/13 because we're looking at the vertical component of that force times 12 inches. And that'll give you FCB. I don't have that value. Yeah, what's up?
So I just wanted to check that By and Bx are just components of FCB.
Yes, yeah. Bx and By are just components of FCB. Is that okay with everyone? Yeah, I just called them Bx and By just because we're at point B. Yeah.
Do you have to take another moment? If you have By and Bx's value, can't you just use Pythagorean?
Yeah. So I'm saying if you didn't want to do the Bx By, sorry, I'll clarify. If you didn't want to do the bx by method, and you just wanted to say, screw it, I'm just going to find FCB, you could use this method, and that'll give you whatever value for FCB. If you do want to show, excuse me, I'm sorry. If you do use the bx by equation, not equation, method, and you still want to show what FCB is, you're going to do exactly right. Yeah, exactly what you were saying. FCB equals square root of bx squared plus by squared, and that'll give you whatever, and these two answers will be the exact same thing. Does that make sense to everyone? Does anyone have any questions on that? Either method is correct. Either method will give you the same values, and then if you want to find, if you use this method, the triangle, the Pythagorean theorem triangle method, and you want to find what the bx and by components of FCB are, you can just, once you find FCB, you could say, okay, by is 5/13 FBC, bx is 12/13 of FCB, and then those are your bx and by values. Does that make sense to everyone? Yeah? All right, cool. So that's all that problem is asking for. That's a typical frame problem. Does anyone have any other questions on frames, how to set them up, how to find reactions, how to conduct analysis on a single member of all the forces on a single member, and the two methods, the triangle and the components methods that we did? No? All right, cool. I'll get out of your way because I see some people are trying to peek around me. Is everyone okay if I erase at least this left board to start? Yeah, what's up? All right, can I take a peek? We'll chat amongst yourselves. He does the like the triangle way? Okay, and you have Williams?
Yeah.
First off, my condolences. Just kidding, I didn't say that, it's fine.
No, it's okay. Thank you, I appreciate it.
Sorry, I'm like totally blanking. All right, 12/13
So
for BC.
I ended up with BC total being 195.
Okay.
Because there, and then 5/13 times 195. I ended up getting 75 for this, so these two canceled out. And then I don't know how I got that though. That was the one thing I was confused about.
Okay, so you got 125.
Yeah, we have some of the forces in the Y. You have plus 50 for BY, and my BY I found to be 75, which is why I'm confused. Because I don't think I messed up any of the values.
So you got BY is, you have 70, 600. Did you 13? Oh no, BC to this is 13/12 of 180. Wait.
Right, because you multiply it.
It should be 12/15. Oh no, 13. You're right. I'm an idiot. Ignore me. Ignore me. I'm just an idiot. Negative 180. 12/13 of BC.
So when you flip.
Yeah.
Okay.
And 13/12 is 195. That makes sense. Did you do the b squared, bx squared plus by squared, square root of that?
Oh, I did not do that.
I just want to check to see if I got the same. For FCB using the square root. Let me go grab my paper real quick.
Okay, thank you.
Yeah, I have this same sheet. Oh, thank you. I'm an idiot. I get you. I got what you're saying.
Yeah, because I just don't know why I'm getting a different answer, because I thought I did this right.
Yeah, I don't know. You know what? Let's come back at the end,
Okay.
just so I can keep moving and get everyone else out, and then we'll look at that because I'm curious because that your way makes sense. I don't know. Yeah, we'll look at it at the end if that. All right, guys, is everyone good? Was everyone able to copy this down? Yeah? All right, cool. All right, so the next problem that I've got is from the same packet. We're going to be doing a centroid problem. Is everyone okay with that? All right, so we're going to look at this question next. I'm sorry, give me 1 second. All right, so this question next that we've got here, they give you this figure with actually all of the dimensions now. I made sure to put them all on there this time. And it asks you, it says, for the composite area shown, locate YC, which is the distance of the centroid from the y-axis. All right, so for any centroid question that you're going to get, you're going to look at essentially the moments for each of the areas, set that equal to the moment of the total area, and that'll help you find your YC. So the diagram that they've written that they always like to write, total moment is going to equal the moments of the individual areas. So the first thing to do when you've got a problem like this is you want to look at what simple shapes you've got in this composite area, in this figure, and see what you can break up your figure into. So right here, it's pretty easy enough to see that you've got triangle on the right here, you've got your rectangle here, then you've got your circle here. So we're going to call the rectangle is going to be area 1, the triangle is going to be area 2, and the circle is going to be area 3. Is that okay with everyone? Okay, all right, cool. And we're looking at the moments around the y-axis because we're looking for YC. So that's the y component of the centroid. Okay, so what this equation essentially breaks down into, it's going to break out down into is you've got m total. It's going to be equal to m1 plus m2 minus m3. So does everyone know why we're doing minus m3 here? Shout it out because it's a hole exactly. So this being a hole in the middle of the rectangle, in the middle of the composite area here, means that we're going to lose the effect of what that mass's moment would have been. Does that make sense for everyone? Why that is the way it is? All right, cool. So the equation that we're going to be using for this, moment's going to be area times distance from the axis to the centroid. So in this case, it's going to be the total area times yc, which is going to be equal to the area of 1 times the distance from the x-axis to the centroid of 1 plus, that's just a1 y1 plus a2 y2 minus a3, sorry, excuse me, y3. All right. Is that cool with everyone? Does that make sense to everyone? Yeah, cool? All right, cool, great. So for A1, we're looking at that rectangle, right? We've just got 8 inches by 10 inches. It's going to give us 80 inches squared. For A2, we're looking at the triangle, right? Correct? So we've got 1/2 times space times height, which is 1/2 times 8 times 6. That's going to give us 24 inches squared. And then lastly, we've got A3, which is the circle. That's going to be pi r squared, or pi times 2 squared, and that's going to give us 4 pi inches squared. I'm just going to write it in terms of pi until we get to our final answer. Does everyone go with that, with the area formulas? I'm not 100% certain, but those should be given to you on the test. Also, please know those by now. Yeah, please. Yeah. So what we're going to do then is we're going to look at, so we just found A1, A2, and A3. What we're going to do next is we're going to look to find what Y1, Y2, and Y3 are. So and these equations are definitely going to be given to you. So Y1 is the distance from, essentially the Y component of the centroid of area 1. It's the distance from the x-axis to that centroid. Does that make sense, everyone? So we're just looking at this rectangle here, since that's area 1. That y value is going to be, since we're going from the x-axis, it's going to be half of the height for a rectangle. It's going to be half of that distance, so it's going to be half of 8. So we're going to get that y1 equals 4 inches. Is that good for everyone? Yeah? All right, cool. Next, we're looking at y2. That's going to be the y component of the centroid for the triangle. Now for the triangle, again, we're looking at the distance going up from the x-axis. For a triangle, the formula is going to be height over 3, or at least the corresponding distance. So in this case, we're going vertical, so we're going vertically. It's going to be that vertical distance over 3. So our value for that is going to be 8/3 inches. And again, I think that these are going to be given to you on your formula sheet. Have they sent that out to you all yet? Do you know what that's going to look like? No, I'm seeing some no's. Lots of people not saying anything. No? Okay, that's unfortunate. I think I should still have mine from my quiz 3. I'll make sure that I get that out to you as well. If they haven't shown it to you, don't bank on it being there, but I'm pretty sure that they will, because they don't, or at least from what I remember, yeah. You were getting one? Okay, so there you go. I'll send it out again anyways, just to make sure that you guys know what it looks like, and so you can be prepared to see what you're going to expect to have. Yeah. So that's just a formula for a triangle. The centroid is going to be at a distance h over 3. So our h in this case, as we're going away from the x-axis, our h is going to be 8, so it's going to be 8 over 3. Is that okay? Is that cool? All right. Is everyone else good with how we got h over, not h over 3? I'm sorry, 8 over 3. Yeah? All right. No? So, again, that's going to come from a formula. If you've got a triangle, you're trying to find that y value there, and you've got some height, h, and you're taking the moment around this axis, say it's the x-axis, your height y is going to be equal to h over 3. That's just a formula that they'll give you. Yeah, what's up?
Could you explain that for shape 1?
For shape 1? Yeah, so for a rectangle, got height h. It's just going to be, so that's h, this is y. Y is just going to be at h over 2. Yeah. Sorry, I'll rewrite that a little bit more neatly. But that's just the straight up formula there for that. Does that make sense to everyone? Yeah. Yeah.
So just, I understand for the y, but if we're triangle, would it be the same for in the x?
For the x, I believe it's the same for the x. Yeah, I believe so. Because if you were to think about it, it should be the same principle if you're just rotating it. Yeah. I'm like 99% sure. Again, I can actually, I think I might have it with me. Yeah, it is. Yeah. So it's just 1/3, whichever way you're going. Yeah, no problem. Is everyone okay with that? And then, do we have any questions going around? No. All right, cool. And then now we just have to find y3. Let's just try to keep it down a little bit, guys, just so that everyone can make sure they can hear. For y3 for a circle is just going to be the distance from whatever axis you're looking at to the center of the circle. So in this case, they give that to you. That's just this 3 inches here. Does that make sense, everyone? That one's a little bit more, not a little bit more, a lot a bit more straightforward than the other ones. Yeah? Is everyone cool with that? Cool. So now, what we're going to do actually is we're going to take these A1, A2, and A3 values, and we're going to say total area is equal to A1 plus A2 minus A3. So that's going to be our 80 plus our 24 minus our 4 pi. And what we're going to get for that is about 91.4 inches squared. Is everyone cool with that? We're just looking at what the total area of the composite area is. And then we can plug that in. So that's a total. So we're going to be able to plug that in over here. You're going to get 91.4 times YC. Again, this is our target value. This is what we're looking for. This is what we're trying to find. So we're going to set that equal to A1 times Y1. So that's going to be 80 times 4 plus, I'm sorry, we found these as well, plus A2 times Y2. So that's going to be 24 times 8 over 3 minus, again, minus because it's a whole. And that's for the same reason over here why we subtract that 4 pi and why we're subtracting the A through Y through here. It's because it's a whole. Minus 4 pi times 3. And then when you solve that, you're going to get that YC equals 3.79 inches. Is everyone okay with that, how we found that? Some professors might denote YC as Y bar, just as being the location of the centroid. I know that's what they have on the solution guide. They tell you to find YC, and then the solution has Y bar. It's the same value. It's the same concept there that's being represented there. Can you all see it? Can you all get this? Have you all gotten all of this down? Any other questions on that? How we're finding the areas, how we're choosing the signs for the areas, how we're finding our Y values, what those formulas are, where we're getting them from, and then overall just how to do the problem, how to set that up with all the moments and everything. Yeah, what's up?
So if it's y, that's the distance from the y-axis?
If it's y, it's the distance from the x-axis. So yeah. So if you're looking at something like this, so that's a really good question. If you're looking at a point here, this distance is really just your y point. And then if you're looking at this, that's really just your x point. Does that make sense? Yeah. I know it's weird. It's just opposite. Yeah. Does anyone else have any other questions? That was a really good question. Just demonstrating why we use, if we're going from the x-axis, we're looking for that distance, we use y, we're finding yc. We're looking at the y-axis, we're using xc. We're finding xc. Does anyone else have any other questions? Yeah.
Just to be sure, that's 3.79.
Yeah, 3.79. Yep. Any other questions? All right, cool. Do you guys, was there any concept? So that's the end of the quiz that I have. If you guys don't have any other questions and you're feeling confident, feel free to check out, head out, make sure you get your name on these sheets so that I can send everything out to you. Again, I'll write my email. If you guys do want to do more problems, we've got this room for about another 45 minutes until 8 o'clock. Another group's coming in, yeah. Some zero force member problems. How do we feel about that? Yeah? You guys want to see that? All right, so, all right, guys. So what I've got a real quick zero force member problem. It's not from the problems you were given. This is actually from my quiz that I took. I just don't have the full work solutions for the problem, but we can at least look at the zero force member part of it. Is everyone okay if I erase this problem that we've got up here right now? Yeah? All right, cool. Oh, I just erased my email. Oh, well, I'm sorry. Oh, do you guys also want to do a moment of inertia problem as well? I just realized I realized that problem was just centroid. All right, so if you guys want, my last question on my quiz was another centroid problem, so we can run through another quick centroid thing and then do the last part was moment of inertia. How does that sound for you guys? Does that sound good? All right, cool. So my zero force member problem. So the question gives you a truss. It was my first question. It was a truss. So just to give you some idea of what you might be getting, I had a truss, a frame, and then a centroid. I think that's pretty standard for quiz 3. You should expect to see truss, frame, centroid. Oh my God, Jesus Christ. Yeah, and the first part of problem 1 was find all zero force members. It was 3 points out of the 10, negative points for wrong answers. Yeah. So if you're when you're doing your zero force member analysis, it's good that you ask. You want to make sure that you're getting answers that you know are definitely right, because if you don't put the right ones, there's a chance that they'll take off points for putting the wrong ones. Yeah. So if there wasn't enough pressure, there's that too. But I'll throw this truss up on the board for you guys. All right, okay, so this is the trust problem that I was given on my quiz. And then if you guys just want to go further beyond this, you know what, never mind. So first question again was asking us to identify all zero force members. So a zero force member is named very accurately. It's a member that has zero internal force, zero member force. So, you know, that's to say that if we were to like cut it open, we'd get nothing out. There would be no, if we were to draw free body diagrams around a nearby joint that it was connected to, we would get no force coming from that member. Does everyone understand the concept of what that is? Okay, cool. So when you're looking to find one, there's a couple of different things that you're going to want to look for. So spots that are going to be good to look at are going to be locations where, sorry, I want to make sure I express this correctly. It's a very like weird thing to say. points where you know that either fx or fy, one of them is only going to have one term. So just to give you an example of what I'm thinking of, if we look at this corner, point G right here, right? If we draw this out a little bit bigger, got G, we've got point H out here, we've got point E out here, this is G. And if we call these the member forces, we call this FGH, and we call this FGE. That's not an E, that was an H. Let's try again. Let's see if I can do this. FGE, there we go. And then I'm sorry, I forgot we've got the 15 kips here. If we do summation of the forces in the x direction, we'll get a value for FGH, right? It's going to be 15 kips going to the left. Does that make sense to everyone? But if we do the summation Fy, right, we say upwards is positive, and the force in the y direction equals 0, we've got a negative FGE and nothing else, right? We're just looking at force GE, and that's it. So by this equality, you've got force GE equals 0. So that's a zero force member. So that's the kind of stuff that you're going to be looking at. You're going to look for different joints, different points where either Fx or Fy will give you one of the forces is equal to 0. Anyone want to give it a shot at finding another, not even the zero force member, but just another spot where we would have another zero force member? Anyone? Yeah. F, right, exactly. So we're going to look at F. So if we draw out F, I'll draw it down here. We're going to have something like this. We've got F, then we've got our three forces. This is going to be F, DF, this is going to be F, EF, and this is going to be F, HF. And then we've got no force coming at it on the right? So if we do summation of forces in the y direction, we're going to get FDF equals FHF. That's not saying that they can't be 0, but that's just saying, I mean, with the way that the rest of the problem is set up there, it's very unlikely that they will be 0, but we can't say for sure that those are zero force members. We know they're the same value, but that's it. If we do summation fx, you've got, assuming that going to the right is positive, the summation of forces in the x direction equals 0. You're going to get equals negative FEF. So you've got FEF equals 0. And then we know that EF is a zero force member. So exactly, that was very good. That was good. Anyone have, there's one more. Anyone have it? Yeah, just shout it out. Give me the point. What was that? B. Yep, exactly, good. So which member is going to be the zero force member? AB, exactly, good. So just so that everyone else can see what we've got at point B. I'm sorry. Is we've got our reaction force at BY. Not at BY, at B. That's going to be BY. We're going to have our member force for BD. That's going to be FBD. And then we're going to have our member force for AB. That's going to be FAB. And again, summation of forces in the y direction will give us a value for FBD. If we do the summation of the forces in the x direction, we're going to get that FAB equals 0. I just so happen to put all of mine in a direction that they end up being negative. If you want to just simplify for yourself, that's fine. You just say it's 0. I saw you first, and then we'll come to you.
Is there one more?
Where are you looking?
Joint C.
At joint C. So what we've got at joint C, when we look at this, is we've got our 30 kips coming in this way, right? We've got member force CD, we've got member force CE, and then we've got member force AC. Yeah, so we know that CD definitely isn't because it's counteracting that 30 kip force, and then we're going to get that FAC and FCE are equal to each other. We don't know that they're not 0, but we can't definitively say that we are, so they're not explicitly zero force members.
Okay.
Yeah.
So we would have to go to the other joints to find out.
Yeah. The zero force members that they're going to be looking at are by definition are going to be the ones like these three that you explicitly look at. You should be able to just look at it and say that's a zero force member. I saw you, and then we'll come down to you. That's a roller. I'm sorry. Yeah, that's a roller, and then this is a pin right here. Sorry if that wasn't clear. Yeah, what's up?
During my talks with professors on that to identify zero force members, the joint must have external loads or reactionary forces or needs on it. So I don't know.
Must not have.
External. So like for G, there's external forces.
Right. So your professor would say that this wasn't a zero force member.
And then also at B, there's reactionary forces.
Right. Who's your professor?
That's what I'm saying.
Fontaine. Interesting. The way that Bill and I know a lot of the other professors teach it is that it's this. And this is my quiz. I got full credit on that for this.
Yeah, she said that it's you look for two-member parts with no external reactions or forces, and then three-member forces that have a fluidity pair.
Okay. Oh, so what she's telling you is either look for your corners or look for these.
Yeah.
Yeah. So those will if they have no external forces, those will undoubtedly. Those are your guaranteed zero force member, these zero force member. Those aren't the only options. I think that's what she's probably trying to say, but she's not. Yeah. Yeah, what's up?
So it's for force EF.
Force EF, yep.
From point E to F, you have to have 30 kips going the other way. How does that cancel out?
So that could be taken. That'll be taken on entirely. Yeah, by the diagonal ones by EH and ED. Those are going to be taking that 30 kips. Those will probably be taking 15 each, but whatever the split is, they'll be taking the entirety of the 30. So that's something that you could transfer over when you go to do your analysis. You could say, I found over here, I found that EF is a zero force member. When you do if you do a joint analysis here, EF you're going to know is 0.
Okay.
Yeah, so that's another handy trick. That's why it's really good to know what your zero force members are, because when it comes to your analysis, that'll be a really helpful tool to have. Do you guys have any other questions? Yeah.
Can we just finish the analysis then?
I don't have the answer, but we could try. Yeah, okay. I ran another review before this, and I was doing problems for both, back and forth. So I had those worked out. I don't have these worked out. I'm sorry. I can send you guys this, and you guys can go through it on your own if you just want practice working through it. Again, I don't have the work solution, so I'm sorry for that, but I'll definitely let you just have more examples at the very least. This is, by the way, I took MechSolids fall 2017, so last fall. If he gave you any old information from fall 2017, that's from when I took it. Yeah. What's up? Oh, you do?
Yeah.
Oh, shit. Oh, what up? Yeah. So we got some solutions for this problem if you guys want to work through the rest of it. Yeah? Are you okay if I borrow that? Yeah. All right, cool. Thank you. Much appreciated. Okay. All right, cool. Yeah. Oh man, this would have been really nice last fall when I was taking this exam. All right. So if you guys want to go through the rest of this, I know it's a little bit more of a complicated trust problem than what we did before. Not necessarily more complicated, just different. You guys want to check out the rest of it? Yeah. Trusses and frames are definitely good to get the practice with. So okay, yeah. They found the same zero force members that we did, GE, EF, and AB. So we're good there. Checks out. What the rest of the question is asking, it's asking for the forces in members ED. Oh my gosh, what is it? ED, FD, and CD. So it's asking for those 3 forces. Or those three member forces. I'm sorry, excuse me. So does anyone know what our first step is going to be? Anyone? Nah? Reactions. We gotta find, that's not the eraser. We gotta find our reactions at A and B. Because right now we just got those drawn in there, but we don't have their actual values. So in order to do the rest of the analysis, we wanna make sure that we get those actual values. And just a side note that for my exam, when they gave us this figure, they didn't tell us, they didn't draw in the reactions, they didn't say anything in the problem to find the reactions. So that's something you definitely want to make sure that, like, when you see a problem, you're like, okay, if I have to do this, let me find reactions first as a whole before I go into the rest of the problem, just so you don't miss them, because that's something really that can really mess up the rest of the problem for you. Is everyone okay if I erase everything except for the diagram? Yeah, all right, cool. Okay. And then after this, we'll go into a moment of inertia problem, and then I can answer any questions that you guys have as well. How am I doing so far? We good? Is everyone good?
I don't know if most inertia on this quiz.
Oh, nice, solid Pinot, nice. Trying to throw off my review. Okay, cool. So, again, like I said, what we're going to do first is we're going to find our reaction. So we've got AX, AY, and BY, and I'm realizing I didn't give you the dimensions yet. We got 12 feet for the base, and then each of these sections is 16 feet. Guys, let's make sure we just keep it down a little bit. All right, so looking at the reactions, at least for the X direction, pretty straightforward. We've got AX going one way, and we've got the 15, 30, and 30 going the other way. So you guys okay if I just go, like, skip through the formalities? So, you know, you'd have to write out fx equals 0, all that stuff, and I'm just going to say ax equals 30 plus 30 plus 65 is 75 kips. Then for the moments, because now we've got two vertical unknowns, we don't want to go right to fy. The summation of fy, we're going to do the moment, so we're going to do summation moment about a with counterclockwise being positive equals 0. We're going to get a negative 15 at 48 feet because we've got these 3/16s. We've got this 15 here. It's giving us clockwise, so that'll be our negative. Yeah, what's up?
So with the zero force numbers, would you say that, you probably said this, but to kind of recognize it is that they're always kind of a T?
Yeah, a lot of them are going to be at corners or at T's like that because here, you know, you've got nothing here or here counteracting these member forces. You've got nothing here counteracting this member force. There's a chance that you could have an external force like we have here at any of these 3 points, but that's a really great starting place. It's always good to go joint by joint for that, just real quick, and do a check. That's going to be like, oh, like if I look at this one, oh, well, these three have horizontal, these three are vertical. Nothing's a 0 force member there, definitively.
Yeah, I just saw that. I was wondering why you didn't choose H until I kind of like took the diagonal one part.
Right, yeah, exactly. And that's another important part of the 0 force members is that you need to remember that diagonal members, anything that's not on a right angle with itself still has those components. So that's where with something like point H, member EH has a vertical and horizontal component which negates both GH and FH as 0 force members. So everyone good with that? Yeah, all right, cool. Okay, cool, all right. Just gonna run through the rest of this moment real quick. So we've got our negative 15 by 48 minus 30 by 32, and these are just all the forces down the left side. Minus 30 by 16 plus, then we're looking at our by by 12. That's going to give us by equals 180 kips up. So our direction was right. And then just doing Fy, the only other force that we have in the y direction is Ay. So we're going to get that Ay equals 180 kips down. And so again, our direction was correct because I already know the solution and I picked the right one because I cheated. Yeah, everyone good on that? How we found those reactions? All right, cool. I'm going to write them in the figure real quick. Okay, so now I'm gonna sneak over to your phone and get shut off on me. Oh no. Thank you very much. All right, so now we're gonna go through, and again, it was asking us for the member forces in FD, ED, and CD. So what we're gonna do, okay, is again, we're gonna look to make cuts that aren't gonna release too many unknowns, but are still releasing some of the unknowns we want. So one cut that we could make is gonna go right here. Bless you, I'm gonna call this cut AA. So that cut's really good. It's giving us 2 of our members that we want with only releasing 1 more variable. So that's we're still dealing with 3 variables. We've got 3 equations, fx, fy, and moment, right? So that's a really good balance to have. We could go something down like this, right? So I'll call that BB. BB is good because it's getting all 3 of ours out, all 3 of our member forces that we're looking for out, but then we're also introducing a 4th member force there, and we've only got 3 equations. 3 equations plus 4 unknowns is a bad time. So that definitely would be a no-go. That's what I did, and I did not finish the problem. So definitely would, 3 is a good number to have. 2 or 1, also, 1 is a terrible frame or truss, so 1 should not be happening anyways. But 2 is okay, 3 is okay. Those are good numbers to stick with. So looking at that cut that we've got there, looking at the top of the truss, and then we've got point E, point F, point G, and point H. We've got 12 feet and then we've got 16 feet. And then I'm sorry, I forgot to draw our member forces. So like I was saying before, it's always a good idea to, and this is also asking you to state if the members are in tension or compression. So again, if we draw all of our arrows like this, we're assuming that they're all in tension, right? Because if they're trying to pull themselves in, they're actually being stretched. So we're assuming that these are all in tension right now. So any negative numbers that we get, is that we're going to know that that's immediately compression. Is everyone okay with that? All right, cool. So that's going to be FCE. We're going to have FDE. Then we're going to have FDF. All right, cool. So if we take the moment, so again, we're trying to eliminate or reduce the number of unknowns that we're working with in one of our equations to 1. We do, and I'm sorry, I forgot 30 kips here, and, 15 kips here. So summation Fy is going to include all 3 unknowns, right? So that's not something that we want to be doing right now. Yeah?
Sorry, real quick. You just explained why the arrow on the way indicate that it's intention. Play would be compression.
Right, so you're looking at it and you're saying the arrows are going like this. That means it's being compressed. But think of the member force of the way that the member is reacting to the forces being applied to it. If the member is going like this, it's trying to oppose what the external forces are doing. So if we're pulling the member apart, the member is going to say, no, I want to, right, exactly, bless you. It's going to say, no, I want to stay together. The member is going to pull in. So if it's in tension, member forces are going inwards. If it's in compression, the member forces are going to say, no, don't push me. And they're going to push outwards. Right, yeah, exactly. Yeah. So that's something I didn't understand until like last semester when I was doing the reviews. So again, we can jump right to moment. Moment's always a good place to start. We take the moment around point E. We're not going to have to worry about these 2 unknowns. We can look at just this 1 unknown, which is coincidentally one of the ones that were asked to find the problem. So if we do with counterclockwise being positive, we do the summation of moments around about point E. When we set that equal to 0, we're going to get this 15 kips is going to give us a clockwise and thus a negative moment. So that's negative 15 at a distance of 16 feet. And then we're going to get, so right now, this is giving us a positive moment, right? So we're going to say, again, additionally, minus f of df times 12 feet. Somebody saying something? Okay, no, I just want to make sure I'm not missing any questions. So then when we do this, we're going to have negative 15 times 16 divided by positive 12, right? Will we move that over? Yeah.
So I'm noticing for most of these frame questions, when you're solving for moment, you're usually given the distance. Are there any cases in which you're going to have to solve for the moment arm?
I think it's very unlikely. They could give you a problem like that. Yeah, that'd just be a very one-dimensional problem of like, here's everything except for this one distance. I don't see them doing that. I really don't. That's a good thought. They do a lot of problems that are kind of reversible like that. But yeah, for this one, they kind of be holding themselves up into just, here's everything except for one number, go for it. They usually like to give themselves a little bit of variability with that. But good question, though. But okay, so we're going to get from here, we're going to get FDF equals negative 20 kips. So what does that negative mean? Compression, right. Right, yeah, so exactly. So remember, with the way that these arrows are going, we assume that all of our members were in tension. Getting a negative number means that we're going to have a member in compression instead. So we've got FDF equals 20 kips compression. And you can just write C for that. So it's wonderful. So there you go. For that one, that's good. There we go. Next up, so we did our moment. We said we're now looking at FY because that's 3. Well, now only 2 unknowns, and we're still looking to get member force ED. So what we can do is this is our only unknown in the x direction, right? So we can do the summation of the forces in the x direction. So if we do, assuming right is positive, the summation of the force in the x direction equals 0. We've got that 15 plus 30 plus, and what we've got here is 12, 16. That's going to end up being 20. We've got another 3, 4, 5 triangle there. It's 3 times 4 times 4 times 4, and then 5 times 4. So we could say that the x component here is 3/5 of the hypotenuse. So that's plus 3/5 times 4. Times 4 is DE. And then this is going to give us force DE, right? I'm hearing it already. I love it. It's going to be 75 kips in compression. And I skipped this middle step here, but that would have given us a negative number for our FDE value, which means that to make it positive, it's going to be in compression. Is everyone cool with that? Someone say no? Or are we good? Yeah? All right, cool. And then from there, so now we've got this member force, we've got this member force. We're still just looking at this member force. So what we can do is we can say, okay, let's look at joint C. If you just look at joint C, I'm going to ignore actually, no, I'm just going to draw everything. We've got, is that E? We've got force C, member force CE, member force AC, member force CD, and then 30 kips. And I'm sure at this point, y'all are pros. Y'all can see that by inspection, FCD equals 30 kips. Does that make sense to everyone? We're just going right to that. So we're just going to get that FCD equals 30 kips. Now, what I did here was different. So over here, right, we assumed everything was in tension. Over here, I have my arrow going the other way, right? I have it going towards the joint. So that means that it's being compressed. Does that make sense? Why that's got to be a compression? Is everyone confused as to why that's compression and not tension? No? All right, cool, cool. All right, cool. So yeah, just again, it's pushing outward, it's saying don't squish me, so it's being compressed. It's in compression and trying to push away from that. And so there you go. There's your answer. Thank you very much for this. I'm gonna steal a picture of what's on the board so that I can fix this for my next time. But thank you very much for that, man. Can I actually take a picture of the second problem as well? I'll just honestly just take a picture of your screen is good enough for me. Just because I also did not do all that part. Thank you again. Let's give them a round of applause, folks. All right, cool. All right, we good to move on to a moment of inertia problem, or do you guys have any other questions about this truss problem, or truss problems in general? No? All right, cool, good. So the only moment of inertia problem that I have right now is from the problems that he gave you guys, if you guys are okay with going over that. So y'all okay with that? Yeah? All right, cool. If you want to follow along with what your handout is, it's just problem 3B. It's the last problem on page 6 of that packet. And I'm just going to run through real quick. You guys all, is everyone, you're all okay if I erase this, everything? Yeah? All right, cool. All right, so I'm going to draw this first. All right, so this is the figure that, sorry, excuse me. This is the figure that you're given in the problem, and it asks you it asks you to determine the moment of inertia of the area shown in figure A about the x-axis. So it's the moment of inertia of this area that I've kind of shaded in a little bit around or about the x-axis. So similar to, or exactly the same as the centroid problem, you're going to want to split your area up into two separate areas. So we're just going to split it up into the circle and the rectangle. So for the circle, so the general equation that you're going to have is your total moment of inertia for an object is going to be equal to the moment of inertia of the shape plus AD squared. Does anyone know what that AD squared comes from? It's a theorem. Exactly. Thank you. I'm sorry. Excuse me. So that comes from the parallel axis theorem, and this is something I don't know if I'm assuming you guys have gone over this in lecture, but something that wasn't really explained to me was like what that does, and that's just essentially acting as an extension of the shape. So not every shape, and in this case we've got it twice. We see it twice. The centroid of the shape that we're going to be working with doesn't lie on the axis about which we're taking our moment of inertia. So the parallel axis theorem is essentially kind of like a correction factor for the shape that you're working with. So it takes into account the area of the shape and the distance it is from the axis that you're working with, that parallel axis, there's where the name comes from, to the parallel axis of centroid to the axis you're taking your moment about, and accounts for that in your total moment of inertia. Because if I'm taking this marker and I'm just spinning it about its center, right, like this, and its moment of inertia is just going to be the moment of inertia of the marker itself. But if it's rotating around my finger like this, I have to take into account the moment of inertia of the marker and that extra distance that I put in between. So it's going to have a much greater moment of inertia than it would if it were just rotating versus spinning around. If it were, I'm sorry, excuse me, rotating about its axis versus rotating around another axis. Does that make sense to everyone? Well, why we have to use the parallel axis theorem? Okay, cool. I just know that was something that wasn't really explained to me in class all that well with Professor Villa. Don't get me wrong, I love him. What? Say that again? He did? He did? Oh, I should have switched. No, I'm just kidding. All right, okay, cool. So we'll look at the circle first. Does anyone know off the top of their head the equation for the moment of inertia of a circle? Feel free, not everyone at once. Whoa. No, I'm just kidding. So for the circle, we've got our moment of inertia about the x-axis is going to be 1/4 pi r to the 4th plus AD squared. Yeah. So what that's going to be in this case is 1/4 pi times, we've got a radius of 25 millimeters, 25 to the 4th, plus, so this area is going to be the area of the circle. So that's going to be pi r squared. So we've got pi times 25 squared. And then this d, this is important, this d is the distance between, the axis and the relative parallel axis or the relative parallel centroid axis of the shape that we're looking at. So in this case, we know that the centroid of a circle is at its center. So if we're saying, okay, this is where the centroid is, we want this distance for our d. That's going to be our d value for the circle at least. So they are so kind enough as to give that to us. We have 75 millimeters there. So we're going to have 75 squared. And that's going to give us 11.4 times 10 to the 6th millimeters to the 4th. Is everyone okay with that? How we found that? Yeah, what's up?
Is it the same for IY? The same 1/4 pi r to the 4th?
Yeah. So for a circle, you'll have this. We're looking at moment of inertia in the x direction, but it'll be the same for the y because a circle's symmetric in that sense. Yeah. And yeah, again, I think that where's my quiz? Yeah, that's worked out on the quiz. So in case you guys are curious, did you have another question? Yeah, you're looking for the moment of inertia about the x-axis. Yeah. Good question, though. So for at least my equation sheet, what I was given, what I have for my formula sheet, they give you the equations for the centroid formula of, I'll just draw them, a shape like this. You've got your semicircle, circle, rectangle, and then they give you a triangle that looks like this. And they gave me the, and hopefully they'll give you the equations for, I'm sorry, not the centroid, but they gave it for IX and IY. And the centroid, I'm sorry. So they give you the equations for IX and IY of each of these shapes along with where the centroid is, which is super clutch. Okay, is everyone cool with that and with this? Yeah? All right, cool. So I'm going to move on to the rectangle. So for the rectangle, we're again going to have pi x equals, does anyone know the moment of inertia of a rectangle? Anyone? What? Base times height cubed. Right, yeah, exactly. We got there, we put it together. So it's going to be 1/12 bh cubed plus, again, ad squared. Now the real question is, does anyone know which one? Obviously, we've got base times. The base is. Ignore. You know what? Stupid question. If you're a mechie, you'll see this a lot in DMC. And if you guys are in D3 right now, you're probably looking at it now. It's very exciting. It's not that exciting. I'm lying to you. But so your base is 100. So your base is going to be whatever is parallel to the axis you're looking at. So we're looking at the x-axis. Our base is parallel to the x-axis. It's 100 millimeters. So we've got 112 times 100 millimeters times our height, which is 75 plus 75. So it's 150 millimeters. And then that's cubed plus the area, which is 100 times 150 times d squared. So again, same concept as with the circle. We're looking for the distance between the axis about which we're taking the moment and the centroidal axis, the relevant parallel centroidal axis of the rectangle. So in this case, it's at the same point again. It's halfway up the rectangle, so it's at the same distance as the circles. It's just, again, 75 millimeters that they were oh so kind to give to us. So that's going to be times 75 squared. And for that one, we're going to get 112.5 times times 10 to the 6th millimeters to the 4th. Is everyone okay with that? How we got that? Same exact process for each. You just need to make sure that you're using the right area and diameter for each, not diameter, distance for each, and then the correct moment of inertia equations. And again, all will be given to you as long as you make sure you're taking them relative to the correct axis. Yeah. Yeah. So it's asking for the total moment of inertia for the area. So you're right, it will be negative. In this case, we're just looking at what that value will be just for a circle. But if we're looking for this one specifically, you're right. We would say that it'll have a negative effect on the total moment of inertia. So right, you're correct. This wouldn't be incorrect, and they also wouldn't say that you're wrong for putting a negative. Because in this sense, we're just showing the magnitude of it. If you write the negative, you're just saying, oh, I understand that this will be a negative later on. So there's no problem there saying either way. All right, lastly, we're going to do the summation. It's going to be the rectangle minus a circle. So everyone good with why we're doing that? The rectangle's present, the circle's a whole. So we're going to do rectangle. So we'll do I of the rectangle minus I of the circle, which is going to equal 101 times 10 to the 6th millimeters to the 4th. Yes. Yep. And there you go. That's your moment of inertia problem. You guys have any other questions? I wish I could. I'm sorry. The test will likely still happen. Yeah.
So you said that d squared is the distance from the axis. Rectangle from the axis is the distance from the centroid?
It's the distance from this axis that passes through the centroid to this one. So that's where the name parallel axis theorem comes from. You're looking at these two parallel axes. Yeah. Okay. Good question, though. Really good question, though. Does anyone else have any other questions? All right. If you guys, yeah, we'll talk about yours. If you guys do have any other questions, I'm gonna be up for a while. I got a lot of work to do tomorrow. So I'll throw my email on the board again. Make sure you guys get your names on the sign-in sheets just so that I can send you everything I've got. Good luck tomorrow, guys. I know the weather's really shitty, but don't let it get you down. 8 a.m. bright and early. It's gonna be a great day. Good luck again, everyone.